Before we move on to the constitutive equation, I wanted to back up a little bit and say a little more about the conservation of, in quotation marks, anything. So the point of this page now is to talk about how we get from the integral form of conservation of a quantity to the differential form. And I skipped over that when we talked about conservation of mass and momentum, but I wanted to give a little bit of a sense of how this works. So we can write the total changes of a quantity in a certain volume. Has to be the changes inside the volume plus whatever goes into it minus whatever comes out. And so we can write this as d by dt, and now we do the volume integral over some quantity, and so this is a material volume, and we write the changes inside as a integral over the some source term s dv, and then what goes in and what comes out is concerned with flux through the surface boundary. So here we call this some C dot N dA. Yeah, so this would be the flux through the surface boundary. And in that case, C is surface sinks or sources, and S here is volume sinks or sources. And this V here is a material volume. Now we have two volume integrals and one surface integral, but using Gauss's divergence theorem we can actually write this surface integral also as a volume integral. So this third term here is V, and it's just the divergence of C dV. Now we can express the left-hand side slightly different using Reynolds' theorem. So let's say we'll use Reynolds here. In that case, d by dt of the integral of f dv v df dt dv plus area integral f u dot n dA. So here I've just given the Reynolds transport theorem. And again, using Gauss's theorem, we can rewrite this as a volume integral, namely the divergence of f times u dv. This term here doesn't change. Okay, the divergence term over here we can express as u dot grad f plus f times the divergence of u. So let me spell this out. That term splits into these two, dv. And now we realize that these two terms really are just the material derivative df dt. So now we can write equation 1 up here. The right-hand side of equation 1, so terms 2 and 3, over to the left-hand side, and then we just have one volume integral, namely df dt plus f divergence of u. So that's from equation 2 here, and then minus s minus divergence of c, and that's from equation 1 up top. dv is 0. And for an integral over a finite volume v to be 0 for all cases, the integrand itself has to be 0. And that is how we get to our differential form. Integrand has to be 0. So we can write df dt plus f divergence of u equals s plus divergence of c. Yeah, where the right-hand terms are our sinks and sources, and the left-hand term is the change in f. And this is our differential form of the conservation of an arbitrary field f here. And up top here we had the integral form. And I'll talk quickly about what examples we have for these different f, s, and c. So f could be, for example, mass. We've had that already. In that case, there is no volume sources or sinks. There's also really no surface sources or sinks, since f is integrated over a material volume, so mass is conserved. So the right-hand side is 0, as we showed a couple of lectures ago. What about salt, for example? Salt can have sources like rain and evaporation in the S term, and then out of the boundary you could have, for example, diffusion across the surface boundary. Another example is heat. Heat would dissipate within the volume, and then it can also diffuse out of the volume or radiate. Another example would be algae. Algae would grow, die, or could be predated on, and they can also diffuse into or out of the domain, out of your volume. And then finally, what we've already talked about, momentum. A source term for momentum, the volume force is G, and then the surface forces would be stress. And stresses can be either due to pressure or viscous stresses. Good, and this gives us an idea of what quantities S, C, and F represent.